As this seminar is part of the UTC Institute of Advanced Systems Engineering seminar series, so you can register for the seminar series. Feel free to sign in there and please fill out your surveys. So we'll start. I'll keep my introduction very brief. This time we have Amit Surana from UTRC. He did his PhD from MIT in mechanical engineering. His expertise are in controls, and recently he'll talk about data-driven operators, data-driven control, and hopefully there'll be a lot of interesting questions from you guys. Without further ado, I'll let him take the stage.
Thanks for the introduction. Good afternoon. Thanks everybody for coming. It's a really pleasure to be here. So I'm going to speak about this data-driven operator theoretic framework, which comes from the Dynamical Systems background. And I believe not many people really have the background for that, so I'll go a little bit into introduction about what this approach is, and then kind of show some applications for nonlinear systems and controls. So as you know, or may not know, UTRC, where I am, belongs to United Technologies Corporation, which has business in the area of building and aerospace technologies, Pratt & Whitney, Carrier, refrigeration, air conditioning, Otis elevators, United Technologies Aerospace Systems, all are part of UTC. So what you may not know is, in addition to making these products, we actually also provide services for maintaining and repairing these products, right? And traditionally, all the maintenance was time-based. You go and look at these systems at regular times. But with the availability of all the sensing and the data, the trend has shifted towards condition-based maintenance. You collect data, you try to understand the health of the system, and then make inference about maintenance and repair, right? So in dealing with these data-driven applications, we are kind of posed with all the 4 V's which characterize the big data challenges, right? So you may think of one engine may have few sensors and that data is not very large, but if that engine flies for many different flights and you have a fleet of engine, then this data starts exploding, right? And so we get into this volume issue, and there's no point looking at one engine data. Really, you can get the insights and inference when you look at all the data. So that's really the issue of the volume. A lot of engine applications are offline. You fly the engine, you collect the data, you do analysis, right? Some applications in UTC have data in motion, right? When you have buildings, the data is streaming, you want to do diagnostics and prognostics, so that's more streaming analytics kind of problem. Similarly, in autonomous intelligence robotic systems, you have large amounts of data from LiDAR, video, all streaming, you do kind of machine learning analytics on that. And pretty much all data problems we have are mixed. There will be structured, unstructured data, discrete, continuous, categorical. And finally, the data in doubt, right? There's a lot of errors in the data, missing data, right? So all the problems we face have these 4 challenges. So there's a whole machine learning group within UTRC which looks at this problem more from the conventional machine learning side, Bayesian maths, deep learning is a topic, human-machine interaction, how humans analyze the data. My interests are in looking at more an interdisciplinary approach, how dynamical systems control trading machine learning can deal with especially data in a streaming setting, high-dimensional continuous data. So let me give you a very quick background about, maybe one step back. So what is the unifying framework? So what I want to describe today is an operator theoretic approach, which I believe will be a unifying framework for that, right? So if you look at dynamical systems, which you have studied in your coursework long back, there are different views to analyzing the dynamics, right? So if there is a pendulum swinging, its position and velocity, you can look at state versus time, which is the Newtonian viewpoint, right? There's a Poincare viewpoint, which we traditionally study in dynamical systems, where you look at the interface space, the position and displacement. And then there's the Wiener spectral viewpoint. If you look at this data, there's one frequency at which there's oscillations. So what you may not be familiar with is another viewpoint, which is Koopman Operator, which is study of dynamics of observables. So you define functions on the state space of position, and you study how those functions evolve under the dynamics. And I'll go into detail what precisely mean by that. And the point is that this operator theoretic viewpoint actually subsumes all these different viewpoints. That representation can allow you to go for state versus time. You can spread that into a point array viewpoint, or you can think of it as spectral viewpoint. And so, and this background is, I mean, this approach is very, I would say, versatile. You can use it for machine learning for time series applications like forecasting, feature generation, for data-driven systems and controls. It can also be used for signal processing like background subtraction, decomposing in general the signal. And I'll talk about all these. So in the first part of the talk, I want to focus how you can do apply these concepts of data-driven systems and controls, right? So one of the fundamental ideas in nonlinear controls is, say you have a nonlinear system, so X is your state, U is your control, Y is your output, multi-input, multi-output, I'm restricting to control or feed nonlinear systems, right? Is to transform this nonlinear problem into simpler forms like bilinear, Lipschitz, and then do your design of analysis and control. So what are the bigger challenges that most of the approaches in literature rely you on knowing those equations to make these transformations? And a lot of these transformations are very difficult to compute. They satisfy very complex PDEs, for example, if you want to derive observer forms with input-output injection errors, for instance, if you're familiar with that. And what I want to argue is that this operator theoretic framework will allow you to construct these transformations in a purely data-driven fashion so that you don't need these equations, which is, when you deal with complex systems, that's usually the case, right? So let's start with what is Koopman Operator. So the geometric viewpoint, so we are studying a dynamical system, which is x dot is fx, an ordinary differential equation. This is the flow map, which is just encoding all the solutions starting from x0. And the geometric viewpoint is to study the invariant manifolds in this space, the stability of those, how they interconnect, and things like that. So the operator theoretic viewpoint is you define a space of functions on this manifold where your state lives. These functions can be complex valued, and these are scalar functions, and you define an operator, which is a semi-group parameterized by time t, which maps these functions to another function, which through this composition operator. So ut psi is another function, which when evaluated at x is just the composition of the function with the flow map. So this is a linear operator, you can check, very simple to say, it's infinite dimensional though, right? So anyway, so it's linear. So you can talk about, just like for the matrix, eigenvalues and eigenvectors, you can talk about eigenfunctions and eigenvalues of a linear operator, right? So they satisfy this equation, ut of p is e to the power lambda times p. Lambda are the Koopman eigenvalues. I'm just showing them in the complex plane, e to the power lambda. They capture the growth and the decay of the dynamics. And these eigenfunctions are defined on the state space. And they kind of capture the phase space geometry, and I'll explain what it means. For instance, if you look at level set of some specific Koopman eigenfunctions, they will give you the basins of attractions of a fixed point, for instance, right? And the question is, when you go from this to this, do you lose any information? The idea is no, right? These are equivalent representations. So to give you just very non-formally, right? These are all formal results, what I'm stating here. So the Koopman spectra contains eigenvalues of linearization of fixed point, for instance. It contains the flow k exponents of them, etc. It contains the Lyapunov exponents if you have chaotic systems. The spectra of Koopman operator contains all kinds of behaviors you will see in this nonlinear system. If you take sufficient intersection of these level sets, you'll actually get the solution of the nonlinear equation, right? So the whole solution space is encoded in these eigenfunctions. Again, these are all formally shown. I'm not going into that. They can characterize the basins of attraction, isostables, isochrones, ergodic partitions. So isostable will mean a set of points which converge to an equilibrium at the same rate, for instance. So you can look at certain specific eigenfunctions, and they will characterize this. So the point is, non-formally speaking, these are equivalent, right? The price is here you are working low dimensional space, here you have to work with an infinite dimensional operator, but it is linear. Okay, so let me give you a little intuition. Let's take a linear system, x dot is ax, right? Everybody's familiar with that. Let's look at the left eigenvalue and the eigenvalue and the eigenvector, and let's construct this inner product X with this vector. You get an eigenfunction. You can show that this is a Koopman eigenfunction for this system. If you look at your state, you can decompose your state if you have a full basis in terms of the right eigenvectors, and you can write the decomposition of X as a function of time using this standard equation, right? So these are Koopman eigenfunctions. These are Koopman eigenmodes, which I'll speak a little bit more, and these are the Koopman eigenvalues. But remember, this has only finite many eigenvalues, eigenfunctions. Koopman operator is infinite dimensional. There are infinite many eigenvalues, eigenfunctions. So for instance, if you take product of any of these two eigenvalues, you'll get another eigenfunctions, you'll get another eigenfunction with the eigenvalue lambdas. So you can create as many as you like. So the interesting thing is now this picture exactly generalizes a nonlinear system for any nonlinear function of the state, right? Through this Koopman operator decomposition. So here you have a nonlinear system. These are the Koopman eigenfunctions, just I'm writing the definition. Take any h of x, which is your output, if you're control theory or observable, if you study dynamical systems, which is a p-dimensional vector. Suppose it lies in the basis of these Koopman eigenfunctions, so you can write each component of h of x in the basis, so these are vectors and these are scalars in general complex. You can write the evolution of h along the solutions as in terms of the Koopman mode decomposition. This is exactly same as linear, right? So that's the power of this Koopman operator. If you can compute and work with this, it will allow you to get your linear intuition for nonlinear systems. This is known as Koopman mode decomposition, and these are known as the Koopman modes. These are eigenvectors, right? So remember, Koopman eigenfunctions and eigenvalues are intrinsic to dynamics. They depend on F. And Koopman modes are specific to an observable. It depends on your H. And while these capture growth and decay, they capture the phase space geometry, they kind of capture the spatial correlations between the sets. Okay. So in discrete time, if you have a map instead of an ODE, you can similarly define a Koopman operator just by the composition. You have the same notion of a Koopman mode decomposition. So here I can give you some relation to how it compares to FFT or POD. What's the relation between this Koopman mode decomposition and POD? So if you take a nonlinear system or a linear system, if you look at the solution along a periodic solution of that, so x0 goes to xp minus 1. If you take the FFT of that, these frequencies are the Koopman eigenvalues, and these FFT coefficients are your Koopman modes. Okay. So in that sense, you can think of this as a generalization of FFT, the Koopman mode decomposition generalization, in the sense that in the FFT, all the frequencies lie on the unit circle of the growth, but Koopman eigenvalues actually capture the growth and the decay, right? So they actually capture the transient behavior as well. And it has been numerically shown that it works better than FFT. For instance, when you have, it's less sensitive to the length of the data. FFT is often, for non-periodic decay data, you have a slower decay for FFT, but this has faster because it can capture the transient better. And the smallest frequency resolved is the length of the data in the DFT, but there's theoretically no lower bound on the smallest frequency resolved or the largest period obtained compared to POD. So each of these modes has one frequency, lambda j. So it decouples the signal much nicely. Each mode oscillates with one frequency or grow or decay with one frequency. The POD actually mixes all these different scales. But the price is that these modes are non-orthogonal. POD modes are orthogonal, right? That's the price. You have to pay the price somewhere. And the last thing is that this is actually, it provides you dynamical evolution of your observable directly, right? In a POD is mostly used for, or PCA, whatever you call it, is mostly used for dimensionality reduction. You still need equations to close and obtain the dynamical equation. You can use those modes to project your equations. But here you directly get the evolution of your output because it's a dynamic representation.
How about numerically? Okay. Because orthogonal things are good for numerical computations.
Here is how we compute numerically. That has been, so the idea of Koopman operator was introduced in 1930s. Okay, and only over the last 7-10 years, this area has picked up because now there are very good numerical techniques available to compute the spectral properties of this operator. And remember, it's an infinite dimensional operator. I'm only talking about discrete spectrum. It can have continuous spectrum, resolve in space, but it's still a challenge. It's still a challenge, but a lot of progress has been made in computing the spectral properties of this operator. So for the numerical approaches, we work with a discrete system. Discrete, so xk plus 1 is fxk, the state. It could be map or the flow map. So there are basically 3 categories of approaches to compute the eigenvalues, eigenmodes, and eigenfunctions. One is the generalized Fourier Laplacian approach, where you basically look at time averages, just like FFT, but you have to scale your data and subtract according to certain eigenvalues, but you need to know the eigenvalues for that. The most popular approach are the dynamic mode decomposition and its variants. Basically, they are non-type methods, and there exists necessarily insufficient conditions. When you actually compute, you will get the Koopman properties. And the most recent is extended DMD, and I'll talk a little bit more about it. But the fundamental idea is to approximate this operator, you need to choose a function basis. That's the key. You choose a function basis, you represent any observable in these bases, so A and A bar are the coefficients. You see how K maps H to H bar, that's the definition. And you get essentially this equation, and then you do a least square on that to compute K, which is a finite dimensional approximation to your infinite dimensional operator in that chosen basis, right? And to be more specific, assume you have your simulation data, XM and one time step of your simulation, of your model. No need for equations, it will come from simulation or experiment. You have selected your basis, and you basically construct these gram matrices. You compute you compute the left and the right eigenvalues of this matrix. The right eigenvectors give you approximation to Koopman eigenfunctions, which is just linear combinations of these bases in the zeta coordinates with Koopman eigenvalues lambda I. And looking at the left eigenvector, you can compute the modes for your specific output. Remember, the modes depend on your outputs. The eigenvalues, eigenfunctions are intrinsic to your dynamics. They don't depend on your output, right? So, of course, this approach is not going to scale to high dimensions, right? If X is 5-dimensional and you are going to choose the basis, it's going to, in every dimension, it's just going to explode. So there's a kernel version of this kernel EDMD, which does the kernel trick to form these inner products here in the kernel space. So you avoid explicit construction of your basis, right? The biggest challenge is what's the right choice of basis kernel. This is a problem in whole machine learning, right? You can use some ideas, and we are exploring some of those from machine learning, like cross-validation and other concepts, where you can search over the space of kernel hyperparameters and things like that for better computation. The other concept is challenge is where to sample and how much data you need. That's always a problem. And here, since this theory is more closer to systems approach, you can use system ID concept like persistent excitation, things like that. Again, these are all things work in progress. How to make them formal? These are just ideas. And often in experimental setting, you have limited data. You cannot control how much data you can get, but you can enrich the data using tokens embedding. If you're familiar with that, you do a time delay embedding to construct the phase-space diffeomorphic to your original system, and there are techniques to select the time delay embedding in there. So that way you can enrich your data so that you can better approximate the spectral properties of your operator.
How does this compare with the Gaussian process? Because you can approximate functions like that too, right?
Gaussian processes.
You can do all the kernel stuff, everything.
Yes. I mean, how it compares to?
Yeah.
So here we are trying to approximate the spectral properties of K, which is the operator. You mean how we can use Gaussian process to do that? Or
yeah. How does it compare? Because you compare with orthogonal things and Fourier type stuff, right? So.
Oh, yeah, that's a good question. I haven't seen a study of how it compares in approximate. But ultimately, we want to approximate the underlying dynamical system, right? Gaussian process is not going to give you that. ultimately that's where we are getting to. Right. Here we have assumed there's an underlying dynamical system, and that's what I'm going to get to next, to maybe it will be clearer where the difference may be. Right. So there is a lot of applications of this AMD or DMD approach. They go from fluid mechanics to time series analysis, signal processing, biology application, and this list keeps on growing as the computational approaches become more advanced. In systems and controls, which is the focus of this talk, a very limited application. One of the challenges you see, when I started this talk, it was x not equal to fx. There was no control in that. Most of the theory of Koopman Operator dynamical system goes like that, right? There's no control in that. And there has been some effort now in introducing control into that, because in most applications you apply, even data-driven, you have to deal with control, right? And what I'm going to describe is some of our contribution towards how you can introduce control into this framework and then do all kinds of applications, right? So I'll make some quick remarks. So the key idea is to transform the nonlinear problem into this representation, and this representation is what we call Koopman observer forms, right? These are like related observer forms with a theory. So let phi x and lambda be a Koopman eigenfunction, Koopman eigenvalue, then its complex conjugate is also Koopman eigenfunction, eigenvalue. You can easily verify. If you take the lead derivative of your eigenfunction along the vector field, so x dot is fx, you actually get lambda phi. This is just the definition of Koopman eigenfunction. So if you take the lead derivative of the real and imaginary part, you get this form. Remember, these eigenfunctions are in general complex, eigenvalues are in general eigenfunctions and eigenvalues are in general complex. So let's take a finite dimensional span, phi1 to phi n. I'm just going to define a transformation which basically makes this complex into a real. This is a standard trick. So you replace phi by phi if phi is real. If phi and phi plus 1 are conjugate pairs, you just replace it by 2 times real and minus 2 times imaginary. So that transforms, that defines a transform from state space to this new space. And if there is any observable hx which lies in this finite dimensional span, you can write that in this form. Phi times vi, and which is equal to c times tx, where c is formed from these eigenmodes. Okay? And the last observation is the lead derivative of this transformation is just given by lambda times phi, where lambda is a block diagonal matrix. It's equal to the real, or it's equal to complex. So if you, these are not hard to derive, but you can see in paper and refer. Assume now that you have this system. There is a finite dimensional span, phi1 to phi n, of Koopman eigenfunctions for the autonomous part. Remember, when you have a control, you don't know how to define Koopman eigenfunction. That's no control. So that's why I'm working with autonomous part, where you have know how to define it. And suppose x, your state, and h of x, which is your output, lies in this finite dimensional span. Then using this transformation, which I just described in the last slide, you can transform this nonlinear system into this form. This is exact if all these conditions are true. So A is formed from the Koopman eigenvalues, C is formed from the Koopman modes, Cx are the Koopman modes for x instead of h of x, and G tilde Z is the lead derivative of your transformation along your control directions, right? So we have made some progress, right? This was nonlinear, at least the outputs are linear now, exact. There's some nonlinearity here as well. The other observation is this is typically low dimensional. When you want to unfold this nonlinearity, you typically have to go to a higher dimensional. So this would be typically much higher dimensional than your nonlinear. And often in practice, you will have to do some kind of truncation. And dx may only be computable in a Bayesian of attraction. And it has some challenges, right? Okay, so to see now what we can do with this, let's look at some simpler forms, right? So if there was no control, or if we look at a closed loop control system, you can transform this into an exact linear system, right, in this high dimensional space. The other extreme is, if suppose your phi was, which is this nonlinearity was Lipschitz, you get a Lipschitz nonlinear system. Remember, you can always write this equation as some az times a locally Lipschitz function, but what you have obtained is you have transformed this nonlinear function into linear, which is very important when you do observer design. You won't be otherwise able to do that. And perhaps the most important form is the bilinear form. Right? So if you make this additional assumption that Lg of t lies in the span of these Koopman modes plus a constant, then this system using this transformation becomes a bilinear form B0u, BLGu, Y2. Okay, so now you can use your favorite techniques available in this area for your estimation and control design, right? Most of my examples I'm going to show is for estimator, right? If you are only interested in control with full state feedback, you don't even need these calculations, right? You can relax those. Okay, so let me talk a little bit about, today I'm going to mostly talk about this representation, which applies to problems where there's no control or where you have a closed loop feedback. U is g of x, so your system becomes autonomous in that space. So you are applying this technique to a closed loop system.
So how would you implement it? Suppose you got some u equal to kz or something. Can you go back and implement in terms of x again?
Yes, because you see we have, since the Koopman modes, x lies in the space, x is cx of z. With that assumption. If you cannot do that, then you have to invert this nonlinear function, and you will get your idea in the nonlinear space. So let's talk about the estimator design. Right? You have this nonlinear system. You transform it, you get into the linear space. You can actually now show that if your A and C in this abstract space is observable, your nonlinear system is actually observable in terms of indistinguishability, the Lie algebra conditions of Krenner and others. And so basically your Lie algebra condition becomes a simple algebra condition in this representation. Right? And then you can design a simple observer, Leuenberger-Kalman filter in the Z space. And if A and C is an observable pair, then you can show that your error in your X will converge to true. So what's the advantage, right? So you can always linearize this approved system and do ECAP, right? That's the standard technique. The claim is that this is a more larger, will provide this linear approximation in a larger part of the space, like a basin of attraction, right? So it will be more accurate, and I'll show you some examples for that. The observer forms, if you are familiar with the work in the 70s, 80s by Krenner, they look for similar kind of transformation, but they look for a diffeomorphism, right? So the X and the Z are in the same dimensions. Here we relax it to an immersion. And if you look for such diffeomorphism, they satisfy very complex PDEs, which is very hard to solve. But here, as I've shown, these are more readily computable. There are techniques to compute this transformation using Koopman mode decomposition. And the most important thing is that this is a data-driven equation tree. You don't need equations to get to this form. You just look at the data. If you have, under all the caveats that you have excited the system, large enough case space, etc., you will get a good approximation. And if you're familiar with cardinal linearization, I don't know how many of you are familiar, that also tries to transform these nonlinear systems, which are analytic vector fields, into, by introducing polynomial tensor products of polynomial as a transformation into a linear or bilinear form. But you will get a very high dimensional system to get a good accuracy. Right? With this Koopman eigenfunctions for this transformation, it will be more compact and more accurate. So again, these are all claims or observations, no theory yet to prove all these things with this topic. Research. So now let me show you an example starting with a simple. So this is your nonlinear system. You want to design an estimator, right? You have an observation y, which is one dimension. You want to estimate x. In this case, you can find a basis phi1, phi2, phi3, which are Koopman eigenfunctions with these eigenvalues, such that your x and h of x lie in that span. You can exactly compute the Koopman observer form A and C and Cx. So these are results comparing what we call Koopman-Kalman filter. So this is linear, you can apply Kalman filter on that. And I'm comparing it to the EKF, which is the extended Kalman filter based on linearization. Right? So what you're seeing in this plot is I've added noise here with two different noise levels. And I'm basically initializing both the filters as same initial condition and running them, and I'm just plotting the error in your state estimate for the KKF and for the EKF at each time point. Right? So these are average of 100 simulations, noise realizations at any time point. And here you can see the KKF has much better transient performance compared to EKF. And this is one of the time traces. So essentially, this is the actual output, this is the noisy output. We compare the KKF with EKF, both are initialized at the same point, and then you can see the response is definitely much better.
This somehow means that Koopman filter is able to identify something much more fundamental than what you would otherwise identify using.
Yeah, and the reason is it is also not only estimating X, it's also estimating X squared. Okay. So let me give you a little bit more complex example. So this is a Van oscillator in reverse time. So the fixed point is stable, the limit cycle is unstable. Right? These are the equations, same output equations. Here we cannot analytically compute that Koopman observer form, you apply numerical techniques. Here I'm just plotting the different number of terms you retain in your truncation and how the error goes with the function of time with the different order. N is the number of terms. So around 25 you can, after you don't have any more significant. So you transform this two-dimensional system into a 25-dimensional system. These are again the results of KKF, EKF, same thing, and you get much better response using KKF. But one point to note here, since this limit cycle is unstable, and I'm just randomly initializing anywhere the initial condition, EKF actually diverges 21% of time for low noise, and for high noise it kind of acts as a stabilizing.
I don't know whether it is a fair comparison though. Mm-hmm. Because EKF probably runs at a fraction of the time your stuff does, right?
So time is there, but yeah, in terms of accuracy. But this is again.
Yeah, so you should have basically compared with things that take the same time, such as particle filters or something. Have you tried that?
Particle filter, not yet, but that's definitely one thing to compare against. Yeah. But
because I think
this is mostly about the representation, right? Whether linearized versus this linear transform, which one works better, right?
So what is the speed up between EKF and your algorithm? How long does it take?
I think
to do
25-dimensional will not be that different, right? It's running a Koopman filter, linear Koopman filter. You're not linearizing or anything, right? So it should not be. I mean, in EKF, if you're linearizing along the trajectory, this is a simple model you have analytical forms, but in more complex systems, that would also be not easy to obtain, right? So yeah, so I agree. It's not completely fair in terms of speed up, but here we are just seeing if there's any advantage in terms of accuracy, right? And the KKF here converges for everywhere, right? Because we have more global approximation. This approach can be used for sensor selection. So again, you have this nonlinear system, you get the Koopman observer form, you want to find the best subset of sensors, so you basically want to split your C matrix into what you observe, what you not observe, so that you can select the best subset of sensors to estimate other sensors. Again, the idea is, since this is a linear representation, you can use linear concepts of observability, Gramian, and error covariance for sensor selection in context of nonlinear system in this transform space. Some of the things, desirable properties of this matrix, right? It should incorporate model error, sensor noise, which error covariance will do. But these matrices are not invariant to sensor scaling. What I mean by that, if I change the unit of the measurement, my sensor selection results will change. For example, if I'm looking at the trace of the covariance of the Riccati matrix, right? You don't want sensor selection to change just based on unit because you really capture a lot of correlations. And these are all discrete optimization problems, right? Objective functions should be somehow amenable to efficient heuristics. So here is one such matrix which has these properties. So it's a slide, it's basically mutual information between the steady state error based on the Riccati equation of what you observe versus what you don't observe. So this is invariant to scaling which you can test. And it still remains to be shown as submodular, but it behaves like submodular, which is basically objective functions which have diminishing return. Right. So you can design now efficient heuristics if you work with this objective, like greedy is optimal for submodular, if you're familiar with that. So I'll just show you one example. This is a chiller problem. The goal is to select the best subset of sensors, which are like the toner, the entering water temperature, leaving water temperature, so that you can best estimate your chiller power. We don't have any models, we just get data from the system. We learn this Koopman observer form from the data, we apply this heuristic based on that metric, and this gives you the sensor ranking. So the way to read this plot is, if you were to select only one sensor, then ton R is the best, and it makes your system observable, the Koopman observer form. If you had two sensors you could select, you can add this one, and that will give you the best accuracy in estimate of your U, and so on. And at a certain point you see diminishing return. There's no point in adding more sensor, right? So this is the way how you could apply this Koopman observer form approach, derive your model from the data, and then from the data determine the sensors are most appropriate for your application. Right? So, yeah.
So can you go back for the chiller plant?
Yeah.
So the as you are progressing, is that the new sensor that you are adding?
Yes, exactly.
Okay.
Yeah, so you add this to this, then you add this to this.
So the third sensor, it doesn't have observability? That's the reason.
No, it's already observable.
I know, but why didn't it pick the third one? Because it's delta is a lot higher.
That's because I was. This is a constraint. I want to select only the one sensor, right? And this is actually the most correlated to the sensor.
So when you're doing the analysis, you have availability of all the sensors, and you're just saying that if I had chance to pick only one,
yes, that would be the best.
Which one would it be, and what's the correlation? Okay.
That doesn't make sense to me, whatever you said.
So this is greedy, right? This is greedy modular approach. Basically,
Yeah, but if you look at from 2 to 3, there's a huge difference, right? In terms of your metric.
yes.
So why didn't I pick that as the first one?
Why did it pick that?
Why didn't I pick that as the first one?
Probably.
So if you didn't have this, I don't think you will behave this will behave as.
So unless you don't have observability or something.
Yes. So this makes it observable, and everything is observable that as well. But that's a good question. So, but physically, if you talk to people who work on chillers, this is the sensor which is most correlated with the chiller power. And if you show them, this kind of makes sense to them physically. I'm just purely doing it from mathematical perspective.
That's the definition, though, right?
Which one?
Ton R is correlated to chiller power. If chiller power is an input, ton R is essentially the effective duty of the chiller. And it's correlated through the coefficient of performance through the system. So it's directly related.
So that's why I picked it.
Yeah,
first.
that's what makes
So
it
physically
observable,
it makes
because it's just the physical one you need.
Yeah.
Okay.
Okay, so now I want to, in I guess next 10 minutes, talk about some machine learning applications, right? So we're focusing how you can use this operator theory for data-driven systems and controls. I didn't show you how you can design controllers using that, but we're working on that. I mostly showed you estimation and subsystem ID. In terms of machine learning, I want to give you some ideas of how this approach can be used for problems like forecasting, anomaly detection, automatic feature generation, positive inference, right? So if you look at time series analysis, right, the classical approaches of ECA, theory, Fourier, they have some deficiencies because, like you work with Bayesian nets, you have to discretize your system. Often you can work with temporal Bayesian nets, but they're very difficult to train in practice. So there are dynamic Bayesian nets like that, right? So I'm talking about these top things, which are most commonly used things, right? Often you have to do handcrafted feature selection to reduce the dimensionality of your data. And the most important, a lot of these approaches like ECPOD don't capture the transients and nonlinearities in your data.
Although the deep learning guys claim that they don't need feature selection, right?
Yeah, so there are these enablers, I'm saying. Right? So these are classical approaches that are enablers in machine learning, like recurrent neural network will capture nonlinear transients. Dynamic Bayesian networks will not require, they will capture temporal aspects. Mixed Bayesian networks will do work continuous. Right? So I'm just suggesting here is that by using Koopman observer form as a generated model of time series, and by combining the machine learning and classical fault detection and isolation techniques, you can also deal with time series. Right? That's what I wanted to show. And let me just give you an example. So this is, for instance, a power grid model. It's a set of nonlinear ODEs. I guess this is the angle of the generator. And this is, I guess, the rate of rotation is just a swing equations, which describe the behavior. So this is, I think, an 18-dimensional system. Now, so what we did is we just simulated the system, get some traces starting at different initial conditions, applied, did some time-bill embedding to make the data more richer, and applied the DMD type approaches to identify the Koopman observer form, and then we kind of test the system for forecasting, prediction, and I guess fault detection and isolation. So in this movie, you'll see the blue things are what you are, so red things are what you measure, the magenta things is your forecast, the black things is the ground truth because it's simulation, and the blue things is what you estimate and then forecast. So this is purely data driven. I'm not using any equations, just simulate the equations, get the model, and then do the estimation and forecasting. Or prediction, as they would call it in machine learning. Then I just want to show you a fault detection example. So at some point, I think around here, we introduce a fault in the sensor. Again, these are all the things you're measuring. This is what you're estimating. And we are using the Koopman observer form with common filter and using the standard FDI techniques, looking at the innovation error and doing hypothesis testing on that. This is where we introduce the error, and it's able to pick that. And of course, your sensors, which were faulty, your estimates become have huge errors, and at some point, the system stabilizes. So again, the point was your system was nonlinear. We transformed into this linear form and applied linear concepts of common filter-based FDI to a nonlinear system. That's the whole idea. Okay, so let me next move to a time series classification example. So to be able to develop that concept of classification, you need to kind of define a distance or a way to compare two time series, right? So if you had these two nonlinear systems and you produce these two time series from which you obtain these Koopman modes and eigenvalues, you can define a variety of matrix to compare these two different representations. So one such approach is you transform these eigenvalues, which in general are complex, so this is complex plane, these are the magnitude of the modes, as a distribution on the space of the eigenvalues in the complex plane. Okay, so that's the point on the complex plane, and this is the kind of the probability of the magnitude. So you have these two different spectra representation of your data. You can define an Arp-Moore's distance between the two distributions as a measure of the distance between these two representations. Right? And there are ways like you can use linear programming to solve this is Mallow's distance or Moore's distance, or versus time metric. The other approach is more system theoretic. So you have these linear representation, A1, C1, A2, C2, with Koopman observer form. You can compare these two models using what is known as Martin distance. Essentially, if you look at the observability spaces of these two systems, and you these are linear subspaces in some high-dimensional space, you compute the angles between them. That gives you how far they are. And that can be computed by solving the Lyapunov equation, doing some eigenvalue computations, and doing that. So there are other measures you can define in this Koopman space representation. So assume you have that representation. We're going to show next how you can generate or use this for automatic feature generation for time series classification problem. So you have a bunch of time series, you want to classify them. So these could be, in the next example, I will show like people running, walking, and you have some cell phone data, you want to classify the behavior based on time series. So the one thing is, given this data, you have to select the right features to develop the classifier. And often what in machine learning you do is you break these time series into small chunks, and you want to find some representative chunks and use a bag over kind of idea. So if you take each of these time series, we could, or the chunk, we could get a Koopman representation for each of those time series, right? So if you look at all this training data, each of this data maps into this nonlinear manifold, where each point is described by A and C. You have a notion of distance, which is like Martin distance or Knowles distance. Between them, you get this distance matrix in this non-Euclidean space. And then you can apply your favorite manifold learning technique like local linear embedding, multidimensional scaling, if you want to map, to transform this into an Euclidean space where it gets flattened out. You can find clusters now in that space, and you can map that back here into this space. And essentially what it gives you is a code book. Among all these little chunks of time series, you have identified which are the key time series patterns in that data. And then what you do is you take each of this time series, you find the closest word in your code book, and you represent now this whole time series as a bag over this code book. And the histogram over that code book could be, for instance, a feature for your classifier. Okay. So when now you're given a test data, you essentially do the same thing. You get a code book distribution, you get a feature, and you get a predictor. Right? So this is one approach of using the Koopman representation to generating features automatically for your classifier.
How do you select the window size?
Yeah, that's window size, the size of the code book. That's still a design issue. I mean, that probably depends on some physics, if you know about the problem. You have to play with different sizes. Okay, so let's apply this to human activity recognition problem. This is a UCI data. Essentially, you have 9 raw signals, and you can see nonlinear phenomena, a lot of oscillations in the data. This is accelerometer, body total gyro at 50 hertz, 2.6 size window. So in this, they gave the window size already. Window. So this is basically the accuracy in the classifier as a function of size of the code book. So what I'm doing is taking this data, getting this Koopman observer form, doing the feature selection, and I'm comparing it with a linear time invariant representation of the same data and doing the same. Right? So the point is Koopman observer forms captures nonlinear oscillations in the data. And indeed, it gives you much higher accuracy compared to this linear time invariant representation. And
What do you mean by that?
This will be like x is ax, xk plus 1 is ax plus noise, and y is cx in the original x space.
So you didn't try with any of the more sophisticated machine learning stuff, yeah?
So basically, the feature generation is the key here. Right after that, I think I tried many different SVM based, and the SVM gives best. And the only comparison is with the manual expert feature generator. So they came up with 550 features manually by looking at the FFT transforms, very specific about how humans move, look at kurtosis, other statistical properties. So they came up with 550, and they have this kind of a performance which you could achieve automatically. That's the point, right? I didn't have to come and sit and invent these new features. It was determined from the data, and I guess this is the confusion matrix. Okay. So a lot of things, again, I don't have time to go into detail, but a lot of the computations related with Koopman are all matrix algebra, right? And a lot of these can be made parallel, can be run on the cloud. So we have a little cloud within UDRC where we test algorithms, and we have made a lot of the techniques about forecasting, prediction, classification run on clouds in a map-reduced fashion, right? So the point is that these computations are amenable for these kinds of deployment on clouds or parallel computations. I can talk more if you're interested later. So in conclusion, just mention some of the ongoing work. So I mostly talked about systems with no control today, right? One of the questions is if the bilinear form is the most useful form you can obtain from this Koopman observer form. How can you identify that directly from the data? So we're working on that. The other big question you may have is you may have to truncate your models. What's the trade-off between accuracy of truncation and the accuracy, size of your truncation and accuracy of your estimate? So we are working on that. Since these are non-orthogonal, this operator is non-compact. It's not trivial to do that kind of analysis. So it has been challenging. Comparison with other approaches, Kalman linearization, exact approximate linearization feedback. We're still looking into relationship of this approach to those ideas. We are trying to apply it to engine estimation control problems. In terms of more time series, as you know, right? Mostly I talked about time invariant systems, but if you have an explicit time dependent, not control, but a forcing from, you can actually, what's the right theory for Koopman operators? We have recently developed in collaboration with Igor for time dependence, which are periodic, quasi-periodic. There you have a two-parameter family of Koopman operator, which you have to work with to define these decomposition. How you compute that is still challenging. We are working on that. The other problem we have looked at is the causality versus correlation, right? So say you have this system and you just measure y. So here, one of the definitions of causality is x1 causes x2 not x2, so the structure of the equation. So can you, given just the data, identify the causal influence? And it turns out these Koopman eigenfunctions, eigenvalues have some relation to this structure. So if you can obtain from that data, you can get some information about the structure, and then you can use information theoretic measures with the in that space of representation to identify what is causing what, and quantify also with the strength. Right? The signal processing viewpoint I didn't at all talk in my talk today, but we have also applying it for crowd video analysis, right? So for instance, this is a highly crowded space. Conventional computer vision techniques are not going to work here, right? You cannot really track every individual here and try to make inferences. The problem is, for example,
pause, please.
Yeah. So the problem is how you want to segment this flow into regions of different qualitative behavior, detect panic and things like that. So it turns out that you can create a dynamical system out of that. So if you look at the optical flow, right, if you look at optical flow, two images, how the points of same intensity move from one image to other, you can think of in this high density regime, each point or person being as a fluid particle driven by this optical flow. So you get a dynamical system X or equal to Fx, which is now circulating with this flow. So now you have a dynamical system, you can analyze the Koopman spectral properties, and you can look at certain eigenfunctions which will give you this decomposition of this flow into different regions. So this is mostly, you see this dominant pattern, you find these different colors, they are related to compression and rarefaction. When people move, you get compression in some places, and you get rarefaction, even on traffic, when you drive. So these regions, we believe, are related to, I think, compression, and somewhere there's I guess compression is here and there's expansion here. So you can identify these regions, which can then be presented to the security personnel who are analyzing this video to pay attention to those certain parts of the video. So in summary, I think I talked about Koopman operator theory, which is dynamics of observable, how observables defined on a phase space evolve. The key insight is that you have a nonlinear problem which maybe transform it into these simpler forms. The price you have to pay is high dimensional. And the question about what's the computational versus accuracy trade-off needs to be studied. Right? And this is kind of a versatile approach. You can use it for machine learning, data-driven systems control, signal processing, kind of same ideas about Newtonian viewpoint, Poincaré viewpoint, and Venus viewpoint are embedded in this representation. And the approach readily combines with control machine learning techniques. I've shown you through some examples. The key is it's data-driven, model-free. That's the key, right, which makes it practical. It's computable. Still, computation is a big challenge. How you select the right basis for your approximation. That's the key, which is very difficult to know a priori. But that's true in any machine learning problem. It's amenable to scalable. I didn't talk much about that, but because of the matrix algebra behind, you can use a lot of advances in there of randomized techniques, for instance, randomized decomposition to scale. And again, this is a new area in terms of, again, getting interest, and because of this data-driven viewpoint, but still lots of work needs to be done in realizing the full potential and limitations. Thank you.
So, any questions to?
So what are the success stories that you have compared to other machine learning things? I know, like have people compared this with the deep networks?
That's the fight we have in
Okay.
DEC. There's a whole group which does deep learning. We are trying to push this. So this is still under
Gaussian
development.
processes, I think, is another competitor with this.
Yeah, so this is, you see, is very new. It's like
Right.
over a few years. There's lots of work to make it powerful and be ready to compare with TensorFlow kind of implementation.
Right, right,
So
right.
this is still in early stages. We have compared it for some problems. Somewhere this worked better, somewhere deep learning worked better. So nobody's really.
Yeah, I think
at this point.
from a numerical viewpoint, I think the non-orthogonality could be a problem with this thing,
It is, but the computational techniques, that's the recent
They're pretty
advances have been
pretty
trying to deal with that
stable,
challenge.
yeah.
Well, they are stable, but it's the choice of the basis is the key.
Right.
Here. So, I mean, in the end, I should say, right, your problem is non-linear to begin with. So when you make it simple, linear, there's no magic, right? There's a conservation of hassle. Right? This is non-linear. You can get to this form if you can compute these approximations well, and that's where the challenge is. Right? So you just push the problem from non-linear to somewhere else. But in the end, it's non-linear. I should have mentioned that before. But there's promise in terms of these analysis.
Okay, let's thank Amit.